Okay, so for this molecule, okay, drawn by Fisher projection, okay. So for this kind of the structure, okay. So you just the very beginning, don't worry about the stereochemistry, okay. To see try to the name as regular organic molecule, okay. So first we need to look at which substitute group has highest priority, okay. So we have the bromine, methyl, okay. So those are only as prefix. So that means this molecule we need to name as the alkene, okay. So for alkene, okay, so we need to find the longest carbon chain, okay, longest carbon chain, okay. So that's easy mistake, okay. So that's here, okay. Yeah, so that's the longest carbon. If you want to start from this carbon, the same thing, okay. So and then next case, so we need the number of the carbon chain, okay. So we need to give the first substitute group lower number possible. So that's case, okay. So we need number from top to bottom because the first substitute group, okay. So on the second carbon here, okay, this one on third carbon. So that's what we do here. 1, 2, 3, 4, 5, 6 carbon, okay. So that means this compound should name as hexene, okay. Okay, so next, okay, we take care of the substitute group. So there's a 1 methyl group here, 1 methyl group, okay, group, and then 1 bromine here, okay. So 2 methyl group, 1 bromine, and then we put them alphabetic order before the parent name. So that's the 4 bromo, and then 2, 3 dimethyl. Yeah, hexene. All right, okay, so now we come to the most difficult part, okay, so try to assign RS to these 2 star center, okay, we have 2 star center, one's here, okay. So that's a little bit careful, okay. Because we need to give the first substitute group okay, lower number first, okay. So this is if we number from the bottom to up, okay. So the bromine we got third carbon, and this one we got second carbon, okay. So we give kind of the first substitute group lower number, okay. So doesn't matter which one, okay. So if only 2 substitute group, okay, 2 substitute group same distance from both ends, then we give a lower alphabetic order one lower number, okay. So but here this one method already give a lower number, okay. So close to the end of the carbon chain. Okay, so next case, so we try to determine RS for 2 star centers. Okay, so that's keep in mind all the horizontal bond okay actually point towards. Okay, so that means this hydrogen okay actually connected by a wedge bond. Also same thing. Okay, so this hydrogen connected by a wedge bond point towards you. Okay, so now we design the part. Okay, so we do this carbon first. Okay, so so most important is which one, this we have 2 branch here, okay, which one has high priority, okay. So this branch, this carbon connects with 2 carbons, okay, and this branch, okay, connects bromine and those carbon, okay. So that's, bromine has higher atomic number than the carbon, okay. So that means this one will be 1, okay, and then 2, and then 3, okay. So you draw the arc, 1, 2, 2, 2, 2, 3, okay. Looks like counterclockwise, okay. Looks like counterclockwise, okay. But the hydrogen, okay, so lowest priority, okay, point towards, okay, so you need to give opposite assignment, okay, so that should be 3R, okay. Next, okay, so to this one, okay, so another color, okay. Bromine has the highest priority, definitely, okay, and then we come to this branch and this branch, okay. This branch has 2 carbon attached, okay. This branch only 1 carbon, okay. So that means this branch second, and then that's the third, okay. Okay, and then we draw the arc from 1 to 2 and 2 to 3. Okay, so it looks like clockwise. Okay, but the hydrogen point towards you. Okay, so now you give opposite assignment. Okay, so 4S. Yeah, that's the full name. All right. Okay. So then we come to this molecule. Okay. So this one. Okay. So okay. So ask you label all the chiral carbons. Okay. What's those solid man? Yeah, so that's a solid wedge. Okay, so those are solid wedge. Okay, no dash. Okay. All right, and so this molecule, actually there are totally 8 chiral carbons. Okay, so chiral carbon means yeah, 4 different attachments. Okay, sp3 hybridized carbon. Okay, 4 different attachments. Okay, and then label them one by one. Okay, so first one. Yeah. So those four and 8 chiral carbons. Okay, so as long as there are 4 different attachment. Okay, so on one carbon. Okay, so this carbon will be chiral carbon. Okay, so okay, so that's total 8. Okay, so any CC double bond. Okay, CO double bond or kind of CC3 bond. Okay, so whatever those carbon won't be chiral carbon. Okay, because won't have kind of 4 different attachment. Okay. All right, good. Okay. So now we continue the chapter 7. Okay. So again, if you have any questions, just type in the chat window. Okay. So last time we start talk about cyclic alkene. Okay. So first we talk about the 2 chiral centers. Okay, but with the 2 different attachment. Okay. So 2 different substance group, okay, on the ring. And so in this case there are totally 4 steric isomers. Okay, and then 2 pairs of enantiomer. The 2 Cs, okay, so RSSR, okay, a pair of enantiomer, 2 trans SSR, a pair of enantiomers. Okay. And okay, like I said, okay, so we can not only use the cis trans assign the stereochemistry of the cycloalkene, okay, because that cannot cover all the possible the stereoisomers. Okay. Right. And so that's the 2 different kind of the chiral carbons. Okay, so when we come to the 2 same chiral carbon, okay, so 2 same subgroup on the ring, okay, the situation get more complicated. Okay, because if we have 2 same the chiral carbon, 2 same set of subgroup, okay, so there's a possibility we generate kind of methyl compound. Okay, right? Example showed here. That says the 1,2 dimethyl cyclohexene. Okay, so 2 wedge methyl group. Okay, and then if you take first look, you can quickly identify this molecule should be a chiral. Okay, because there's the simply plan cut through this molecule, make left half and then the right half kind of mirror image into each other. Okay, and this one should be methyl compound. Okay. Right. Someone may ask, okay, so this is just you draw like this way, okay, for reality, okay. So this molecule should be the chair conformation, okay. So if the chair conformation, maybe not chiral, okay. Maybe not a chiral, okay. All right, so that's the chair conformation for cis 1,2 cyclohexene, okay. And one bond, both kind of a wedge bond, okay. So that means both point up, okay. And then one has to be kind of equatorial, okay, and then one axial, okay. And in this case, there's no symmetry plan cut through this molecule, okay. Looks like this molecule should be chiral, okay. So no symmetry plan should be chiral, okay. And but don't forget, okay. So we have 2 same symmetry, the 2 same kind of substance, okay. And then you can do a ring flip, okay. So we'll do ring flip, okay, so axial become equatorial, equatorial become axial, okay. And then for both, okay, so if you take second look, okay, you find exactly kind of mirror imaging, right? Okay, so mirror imaging here, okay, so it's kind of match, okay. And then that means both kind of should be chiral, okay. So that means these 2 should be the enantiomer to each other, okay. All right, and the enantiomers, okay, so because we have 2 methyl group, okay, so one equatorial, one axial, okay, so same thing for another enantiomer, one equatorial, one axial, okay. So these 2 will have same energy, okay, and then in the solution, okay, so they quickly do ring flip, okay, and eventually we get kind of 1-to-1 ratio of these 2 components, okay, just for this say the 1,2 dimethyl cyclohexene, okay. And so if it's 1-to-1, okay, so 2 enantiomers, okay, so that's actually same as the A chiral molecule, okay, because it's 1-to-1, okay, so mass up, okay, so we just say same as the A chiral molecule, okay. And here you can write it down, okay. So in a one solution, okay, so if 2 enantiomers, so 2 enantiomers, okay, in 1-to-1 ratio, okay. So the whole solution actually you can treat it as the A chiral, okay? All right. And in this case, yeah, for CC, yeah, 1,2-dimethyl cyclohexene actually kind of yeah, although it's the chiral molecule for individual conformation, but yeah, because of quickly reflip, okay. So overall is A chiral, overall is A chiral, okay. And in other words, okay, so yeah, if we draw flat kind of the planar structure, okay, so what's that structure, okay, so give the same conclusion for the chair conformation, okay, so yeah, chair same conclusion, okay, so both are A chiral. Okay, so yeah, if we move to the trans 1,2-dimethyl cyclohexene, okay, so that's trans, okay, so one wedge, one dash, okay, one going up, one going down, okay. So this one definitely there's no symmetry plan, okay, because one going up, one going down, okay. So this molecule looks like should be the chiral, okay, and it should have its own enantiomer, okay. So the answer is yes, okay. So is the enantiomers 1s, 2s, okay, R2R, okay. So that kind of mirror imaging and non-superimposed, okay. So no matter how do you flip it, okay, how do you rotate, okay. So yeah, won't be kind of superimposable, okay. Right, again, okay, so yeah, we said this molecule should be the real conformation, should be a chair conformation, okay. So let's see what's the chair conformation looks like, okay. So for 1, 2, the trans-dimethyl cyclohexene, okay. So yeah, 2 chair conformation, okay. 1 chair conformation you can put the both the methyl group at the equatorial position, okay. So one going up, one going down, okay. Another one also one going up, one going down, but another one has both the methyl group at kind of the axial position, okay. So we already learned chapter the 6, okay. So yeah, both the axial group is much less stable than the di-equatorial position the conformation, okay. So in the solution, okay, 99% time, okay. So yeah, maybe 95, okay, I will say, okay. So yeah, 1, 2, trans-dimethyl cyclohexene will stay at this conformation, okay. Right, and then also this conformation is also the chiral, okay. So yeah, you cannot find a symmetry plan for it, okay. And overall, okay, because of these two are not mirror imaging to each other, okay, and also not same bond, okay, and then this the most stable conformation is the chiral, okay. So yeah, so overall the whole molecule should be chiral, okay. So same thing for its mirror imaging, okay. So the enantiomers, okay. Right, just one thing keep in mind, okay, so when you do ring flip, okay, cannot change the RS assignment, okay, still RRSS, okay, so whatever, okay. So yeah, won't change, okay, just only change kind of equatorial to axial, axial to equatorial, even won't change kind of pointing, okay. Down is down, okay, going up is going up, okay. And here also another the evidence indicate so for cyclohexene case, if you use this wedge that structure, okay, so give same conclusion for the kind of the chair conformation, okay. So and here's some kind of small conclusion, okay. So yeah, for the cis, okay, so we get kind of methyl compound, only one single compound, okay. And then for trans, okay, so we get a pair of enantiomers, okay, totally 3 stereoisomers, okay. All right, okay, so now give one more example is the 1,4-disactyl cyclohexene, okay. So yeah, for example here the 4-methyl cyclohexene, no, okay. So yeah, we do this one first, okay. So yeah, have 2 different stereocenter, 2 different section group, okay. But there's no stereocenters, okay. No stereocenter, okay, because this carbon has 2 same attachment. This carbon also has same 2 attachment, okay. And so yeah, for 1,4 methyl cyclohexene, no, okay. So overall we have 2 stereoisomers, okay. So one is the cis, one is the trans, okay. And for both actually kind of A chiral, and then both there's the symmetry plan cut through this molecule, okay, like this way, okay. Cut through this methyl carbon and then carbon oxygen, okay. So half can mirror imaging to another half, that means the whole molecule A chiral, okay. Okay, and then it's also same thing for the 1,4-disactyl the 2 same set group. For example, the 2 methyl group, okay, 2 same methyl group, okay, and then there's no the chiral, okay, so A chiral, okay, so symmetry plan cut through, okay. Something to ask now, how about the chair conformation, okay? So chair conformation, I can also show you what it looks like for 1,4-disactyl, okay. Right. So doesn't matter chase 6 trans, okay. So yeah, we just do this, okay. So yeah, for example, here we do 6, okay. Right. Okay. So 2 math, okay. And so yeah, here actually you can also find the simple plan. Okay, simple plan cut through kind of. Let me see. Okay, so yeah, simple plan. Okay, so yeah, cut through this carbon, this carbon, this carbon, and this carbon. Okay, so somehow like this. Yeah. So in this case here, this half. Okay, so here going up, going down, going down. Okay. So mirror image into another half. Hopefully you guys can imagine it. Okay, so yeah, so the whole molecule still a chiral. Okay, so yeah, and so in other words, okay, so yeah, right down here. Okay, so that's important here. Okay, so yeah, if you try to assign the chirality, okay, as chiral A, chiral, or try to assign RS for steric center, or try to compare relationship between two molecules, okay, it's better way to transfer kind of the chair conformation, okay, so to planar, okay, that structure, okay, so that will make your life much easier, okay, so yeah, and yeah, so yeah, give you one example, okay. Yeah, this was actually from last year kind of example quiz, okay. Right. Okay, so here ask you kind of compare the relationship between these two molecules, okay, and both are chair conformation, okay. So yeah, if you take first look, it's hard to determine, okay. So yeah, relationship are they Isomer, Enantiomer, constitutive isomer, all identical, okay. So that's the one typical types of question you'll see in the future exam quiz for chapter 7, okay. Right, okay, so yeah, for this case, okay, so pretty easy to do it, okay, so if you use planar structure, okay, so I call it wedge dash structure, okay, so yeah. Okay, so yeah, that's the two substance group going down, that means kind of dash line, okay, so dash line for OH. Right. So these two both are going up, okay, so yeah, one is kind of the wedge OH, and also wedge the methyl group, okay. So yeah, make sure you label right here relative position, okay. So yeah, the increase for some student kind of suppose 1 4 label as kind of 1 2, okay. So that's here that kind of totally messed up, okay. Right, and then once you convert here both into the wedge that structure, okay. So that's here should be easy identify. These two should be identical, okay. Okay. The reason for that kind of you flip one molecule, okay. Right, like 180 degree, okay. Easy kind of superimposable to another one, okay. So yeah, 180 degrees, okay, and then kind of overlap, okay. So that's here much easier. You try to kind of to see whether superimposable for this chair conformations, okay. So you have to rotate, okay. So think kind of flip the chair conformation. That's much harder, okay. But here for planar kind of much easier, okay. So that's why kind of important tips, okay. So yeah, wherever you see chair conformation, okay, draw planar structure, okay. So that's makes you easy to for the all stereochemistry, okay. Okay, so next we'll talk about the chemical and the physical property of the isomers, okay. So for constitutive isomer, okay, so pretty much a different kind of structures, okay. So like the butene and also this is THF, okay. So the same formula, but different kind of different molecule, okay. And then they have the different physical and also chemical properties, okay. That's easy to understand, okay. And then come kind of stereomers, okay. Stereomers, okay, so they have same connections, okay, but some stereo centers, okay, are same, okay. So for example, this stereo center, okay, so both dash line. Some stereo centers, okay, opposite, okay, so one's dash, one's wedge, okay. So that's their stereomers, okay. So their stereomers, okay, so although they have very similar kind of structure, okay, but they will have very big difference in their kind of physical property and those chemical properties, okay. For example, this is 2R, 3R tartaric acid, and then 2R, 3S tartaric acid, okay. One same, one opposite, okay. And then the melting point, okay, are different, okay, so yeah, quite different, okay. And then even their density are different, okay, so that means kind of yeah, these two, yeah, we should able to distinguish, okay, so yeah, for example, yeah, we take the melting point, okay, and then yeah, they also have yeah, the different physical and chemical properties, different reactions, okay. And then we come to the enantiomers, okay, so enantiomers kind of yeah, they will have the same kind of identical physical properties, okay, in achiral environment, okay, so the same melting point, same boiling point, heat convection, solubility in water. Water is kind of achiral molecule, that's why I call it kind of achiral environment, okay. So one example is 2R, 3R tartaric acid, and then 2S, 3S tartaric acid, okay. So yeah, you can see kind of the both their centers are opposite, okay. So that means here should be enantiomer to each other, okay, and then they have same melting point, okay, and also same density, okay. So that means here for enantiomers cases, it's very challenging, okay, to distinguish two enantiomers, okay. So because two similar structures, okay. So if you really want to distinguish them, kind of you have to put the two enantiomer in a chiral environment, okay. So for example, we use some kind of chiral solvent, okay. So they may have different solubility, okay. Or use some the chiral reagent to have a reaction to the both, okay. So then may have a different reaction rate, okay. And so to distinguish kind of two chiral molecule, okay. So there we can use some kind of special instrument, okay, called the polarimeter, okay. So to learn the parameter, okay, so we have to start with the optically kind of active kind of light, okay. So for the ordinary light, okay, so we just kind of talk a little bit the background information. Ordinary light, okay, so like our sunlight, okay, also kind of lamp light, okay. So the lamp wave, okay, so vibrate all the plants, okay, all the directions, okay. So go this way, this way, this way, or this way, okay. And when it's kind of the propagation, okay, so and plant polarized light, okay, so the light only vibrate in one direction, okay. So one kind of parallel plane, okay. So this one we call the plane polarized light, okay. And for one compound, okay, if it's chiral, okay, it will rotate the plane polarized light, okay. So for certain degrees, okay. So for example, very beginning is here, okay. So once you let the plane polarized light pass through the chiral molecule, okay. So then it will maybe vibrate these two directions, okay. So this kind of compound we call the optically kind of active compound, okay. And actually kind of it's another way we call the chiral molecule, okay. So for the physics, okay, so most kind of time like call the optically active compound, okay. So for our chemistry, so we like call it kind of chiral, achiral, okay. So you can write it down, okay. Chiral actually equals to optically active, okay. So that's actually kind of same thing, okay. Chiral equals to optically active, okay. And in future exam quiz, okay, so if a question asks kind of is this molecule optically active, okay? So that's actually kind of ask you when is this molecule chiral or not, okay? So in other words, okay, so achiral equals to optically inactive, okay? So that's same thing, okay? So that's just the same thing, kind of differently the way to describe it, okay? Just keep in mind. Okay, so now we go to the plane polarized light, okay, so and also use parameter, okay, so to show the RS kind of the enantiomers, okay. Okay, so that's the parameters, okay. So that's normalized, okay. So when the normalized pass through we call the polarizer, okay. So then only one direction kind of the light can pass through, okay. Generally kind of plane polarized light, okay, only this direction, okay. And you put your sample in the sample chamber, okay. So just normally kind of solution or kind of liquid, okay. And then if this the sample is chiral, okay, so it will rotate the plane polarized light, okay. So certain degrees, okay, and then generally kind of specific rotations, okay. So if it's achiral, okay, there's no such rotation, okay. So so that's help you determine one molecule kind of chiral, achiral, okay. and also actually kind of tell you maybe two different kind of enantiomers. Okay, so here's were all the style the parameters. Okay, when I was the student, okay, so I use this kind of kind of just manually kind of you have to adjust some kind of parameters. Okay, and then you can measure this rotation kind of rotation measure kind of rotation angles. Okay, and so nowadays kind of there's more automatic kind of parameters. Okay, so as long as you put your sample cell inside, it automatically tell you what's kind of rotation angles. Okay, all right. Okay, so in the chemistry department, okay, so we have this kind of instrument. Okay, so just manual one. Okay, so all right. Okay, so when you get to the observed rotation, okay, so with certain degrees, okay, actually you can calculate kind of specific rotation. Okay, so specific rotation kind of the special property for chemical compound, chiral compound. Okay, so similar to melting point, boiling point. Okay, so this the data won't be changed. Okay, so different chiral compound will have different specific rotations. Okay, right. So here's the definition for specific rotation. Okay, so observed rotation of one chiral molecule, okay, at concentration of the gram per 100 ml, okay, in the sample tube, okay, 1 decimeter long. Okay, and then so what's the observed rotation will be kind of we call specific rotation. Okay, and you need to be careful. Okay, so if it's the pure liquid, okay, the unit become gram per ml. Okay, so maybe right here. Okay. Because this is the only calculation question in organic chemistry. Okay, so organic chemistry normally don't have calculation questions. Okay, so but here's the only example. Okay. All right. Okay. So when we put kind of the alpha in the parentheses, okay, so the bracket, okay, so that should be this is the specific rotation. Okay. This is the fixed value. Okay, so won't change. Okay, so different chiral molecule has different the specific rotation. Okay, so like a melting point and boiling point. Okay, so last year we can use this one identify certain chiral molecule. Okay, right. So here it's kind of observed. Okay, rotation. So this one you use a parameter to measure. Okay, so observed rotation. Okay, and here's the concentration. Concentration, you need to be careful. Okay. So depends it's a solution or pure liquid. Okay. So if it's the solution, okay, the units here will be a gram per 100 ml. Okay, so a gram kind of the sample dissolving 100 ml of solution. Okay, a solvent. Okay, and then if it's kind of the pure liquid. Okay. So the unit become gram per ml. Okay, so that's to make sure you understand what's difference. Okay, all right, and then this L is kind of the long cell cell. Okay, so normally the units the decimeter. Okay, so so be careful with the units here. Okay, so especially kind of the concentration and also long cell. Okay, and specific rotation and also observed rotation units just the degree. Okay, degree. Okay, and here the lambda means what's the wavelength of the plane polarized light. Okay, so normally that's here we call the D D line. Okay, so that's the sodium lamp. Okay, so D line. This lambda is the wavelength is 589 K nanometer. Okay, so that's most common. Okay, T just normally just room temperature. Okay, okay, so all right, so now I show you the two examples for the calculation of specific rotation. Okay. The first one is tell you kind of I see 2 butyl, okay, placed in the 10 centimeter parametric cell. Okay, so here's the long cell cell. Okay, use D line lamp. Okay, and observed rotation. Okay, at 25 degree, it's plus 104 degree, and the density of the compound is 0.8005. Okay. And so ask what's specific rotation. Okay, so you just implant all this information into the former. Okay, so you get kind of data. Okay, right. Okay, so ask you for the what's specific rotation. Okay, so right? So for the observer rotation 104 degree, okay. So make sure you keep this plus sign, okay, because the RS kind of enantiomer showed kind of different sign, okay. And then concentration is because here we use a pure liquid, okay. So that's here we use the density as the units, okay. So gram per mil, okay. So 0.8, okay. And then gram per mil, okay. Length of cell, okay. So 10 centimeter equal to kind of 1 decimeter, okay. So 1 dm. All right, okay. Next kind of just the calculate, okay. So that's let me see what's the data. Plus 129, okay. Again, okay, so don't ignore this kind of the plus or minus sign, okay, because they show the different kind of the rotation directions, okay. All right, and then show you guys another example, okay. Here ask kind of what's observed rotation, okay. Observed rotation, okay. Keep in mind, okay, this time I ask kind of what's here, this guy, okay. And then of the 0.524 okay, gram of this compound, okay, dissolving 10 ml of your methanol, okay. So now we have solution, okay. So and then the cell loss, okay. So it's 1 decimeter, okay. And the specific rotation this time told you, okay. So 30 degrees, okay. So we here, okay. So on the page. Already told you specific rotation. Ask kind of calculate the observed rotation, okay. So we still can use this formula, okay. So specific rotation, observed rotation divided by concentration times length of cell, okay. So here already told you observed rotation. This time kind of minus 30 degree, okay. And then observed rotation concentration, okay. So concentration told you the 0.5425 gram, okay. So in 10 ml solution, okay. But remember, okay. So here, so if we use solution, okay, should be kind of gram per 100 ml, okay. So that means for the gram per 100 ml, okay, should be 5.425, okay. Right. Okay. So that's for 100 mil, okay. So 100 mil, okay. So for 10 mil, okay. So 100 mil times 10, okay. So that's 5.425, okay. And then length of cell, so still the 1 decimeter, okay. So 1 decimeter, okay. Okay. All right. So now we have all this information. We need to get alpha, okay. So alpha just equals minus 30, okay. So we put this one on the left, okay. So times 5.425, okay. Times 1, okay. So let's come up to minus the 157.3.35, okay, 55, okay, degree, okay. Again, okay, so you need the keep minus sign, okay, because that topic clockwise or counterclockwise. I'll show you in next slide, okay. So don't forget, okay. So make sure you know how to do the calculation, okay. So we'll have a similar question in the coming exam too, okay. Right, okay. So it's how do you use the parameter distinguish two enantiomers, okay. So two enantiomer, okay, so should show the same values of the spectral rotation, but the Z will opposite, okay. So and so one the enantiomer showed kind of the plus, okay, rotated polarized light, okay, clockwise. Another one will rotate kind of counterclockwise, okay. So so if it's rotated kind of clockwise, okay, we call it the dextro rotatory, okay. So we use DO plus, okay. So that's a plus come from, okay. So here, okay. And that's a plus come from, okay. So that's means here the first example, okay. So the sample rotate here polarized clockwise, okay. And if it's counterclockwise, okay, so that's here we call the level rotatory, okay. So use L or minus, okay, indicate, okay. So that's here, okay. So that's minus, okay. That means here the I see two butanol, okay, actually second sample, okay. So rotate polarized counterclockwise, okay. So and so two enantiomers, okay. So they have same value, okay. So for example, this I see the lactic acid, okay, and also the R lactic acid, okay. So both are 2.6, okay. But here the one enantiomer will rotate plan polarized clockwise, okay, so that's the S, okay, so that's use plus sign, okay. Another one rotate kind of here the counterclockwise, so that's here the minus sign, okay. So yeah, so you can say kind of here the same value, but here the just here different kind of directions, okay. So rotate the plan polarized light, okay. And just one thing keep in mind, okay, there's no relationship kind of plus minus, okay, and with the R or S, okay. So yeah, you cannot predict kind of it's rotate the clockwise or counterclockwise, okay, just by look at RS, okay. So yeah, clockwise, counterclockwise really depends kind of real measurement, okay. So yeah, real measurement, okay. So yeah, that has nothing to do with RS, okay. And when you purchase some kind of chemicals, okay, so yeah, sometimes kind of in addition to RS kind of labeled for you, okay, you can see kind of here plus sign or minus sign, okay. So that's actually kind of indicating plan polarized kind of the directions, okay. So yeah, that's here means normally means this molecule is kind of pure chiral molecule, okay, pure chiral molecule. Right, and there's one definition, okay. So yeah, if we have one mixture, okay, with 1-to-1 ratio for the R and S together, okay. So this mixture we call the racemic mixture, okay, racemic mixture, okay. So racemic mixture, okay, so yeah, because the RS, okay, so the spectral rotation cancel out each other, okay. So the spectral rotation kind of 0, okay. So actually racemic mixture kind of the same as we treat it same as the So racemic mixture we also call it racemate, okay. Same as the achiral molecule, okay. Yeah, because there's no spectral rotation, and then there's no some kind of the other chiral molecule behaviors, okay. So for racemic mixture, okay, so normally you label as the DL, okay, or just kind of plus minus, okay, together, okay. So that's how do you label racemic mixture, okay. So that's a mixture kind of last value, okay. So yeah, because you have two enantiomers together, okay. So R 1-to-1, okay. But for some kind of important chemicals, okay. So like some the medicinal drug, okay, or some kind of agriculture kind of product, okay. So has to be chiral one, okay. So yeah, in this case we have to kind of separate the two enantiomers, okay. So this process we call the resolution, okay. Resolution, okay. So yeah, separate the two enantiomers out of a racemic mixture, okay. And that's one of the most difficult challenging in organic chemistry, okay, because there are two enantiomer, two isomers, okay, same melting point, boiling point, okay, and the same chemical property, okay. So yeah, so to separate these two, okay, so yeah, there are several ways to do it, okay. So one's kind of recrystallization, okay. So yeah, we just kind of dear serum, okay. So what's that mean, okay? So show you some kind of small cartoon, okay. Right, so we have a racemate, okay, racemate RS in 1-to-1 ratio, okay. And then we have another the chiral molecule, for example, is R, okay. Okay, and then mix with the RS kind of mixture, okay, and then it will bind the both R and S, okay. It should be S, sorry. One R1, okay. Okay, and then you find, okay, so once you bind it, okay, so you generate kind of dear isomers, right? Okay, so dear isomers, some same, some opposite, okay. So for dear isomer, where I know that kind of they have different properties, different melting point, boiling point, kind of different even polarity, okay. And then that's much easier to separate them kind of dear isomer, okay. So dear isomer much easier to separate kind of the enantiomers, okay. Another is the chiral chromatography, okay. So these two, okay, we just learn the chromatography, okay. So so you instead of the aluminum, okay, so we use some kind of chiral molecule as the stationary phase, okay. So this chiral molecule can only bind one of the enantiomers, okay. So maybe R, maybe S, okay, and then we get kind of separation, okay. And last way to separate the two enantiomers by a symmetrical reaction, okay. So pretty much use some chiral reagent or some kind of catalyst, okay. Or maybe some kind of just enzyme, okay. Try to react with this racemic mixture, okay. So this enzyme or chiral reagent only react with one of them, okay. And then you generate kind of the two different products, okay. So that gets separation, okay. So for the enzyme, okay, so here kind of the small cartoon show why it's kind of the different ability, okay, to react with the two enantiomers, okay. Okay, so for enzyme itself, okay, also the chiral molecule, okay. And then these two are enantiomers to each other. Okay, you can see kind of the aldehyde and alcohol kind of switch the position. We swapped kind of with enantiomers. Okay, and then enzyme can only bind one of the enantiomers. Okay, so you can match. Okay, exactly. Okay, but cannot bind another one. Okay, not match. Okay, so in this case, the enzyme can have reaction only for one enantiomer, not another one. Okay. And for organic chemistry case, so we try to mimic this the process with some of the other chiral region. Okay, so we call it the enzyme mimic or kind of just catalyst. Okay, chiral catalyst. Okay, here's a little bit show off my research. Okay, so so I use some of the chiral cobalt silicon complex. Okay, try to resolve this the two enantiomers. Okay, so that's epoxide. Okay, you don't need to use that. Okay. So you can see that's chiral center, okay, mirror imaging to each other, non-super impossible, okay. Right, and then we apply this this catalyst, okay, that's the chiral the cobalt silicon. So these two enantiomers, okay. So only this catalyst bind with one enantiomers, okay, and then carry reaction, okay, and then generate kind of diol, okay. Another one you leave alone, okay. So in this case here, we have two totally different molecules. Okay, easy to separate these two. Okay, because one's diol, one's kind of just the epoxide. Okay, so even you use the distillation can separate these two. Okay, and but for the very beginning case, so you have two enantiomers. That's hard to separate it. These two same boiling point, melting point, everything the same. Okay, so to tell you, okay, so for this the racemic mixture epoxide. Okay, so probably like $10 you can get 1 kilo. Okay, 1 kilo. Okay, pretty cheap. Okay, but for the chiral the final the molecule. Okay, this one. Okay, like 100 per gram. Okay, 101 gram. Okay, you can see kind of why it's kind of important. You get kind of the separated isolated resolve the two enantiomer, get one pure chiral molecule. Okay, so that's the you can make money actually. Okay. Right, so here are some other chiral compound. Okay, and the first one is we already talked about kind of the chiral compound based on tetrahedral carbon with 4 different attachments. Okay, so that's we learned before. Okay, okay, A, B, C, D, 4 different carbon. And then this chiral carbon, and then this molecule will be chiral. Okay, so in addition to carbon, okay, so other atoms can also be the chiral centers. Okay, and then whole molecule can be the chiral. Okay, one example is the quaternary amine. Okay, so also called ammonium. Okay, so you have 4 different attachments similar to the chiral carbon. So this molecule will also be chiral. Okay. And then the same thing is for the silicon. Okay, silicon, if you have 4 different attachments on the silicon, okay, so this molecule will also be chiral. Okay, and there's one special case called the pyramidal atoms. Okay, so those atoms have a lone pair electron on it. Okay, and then there's a possibility of generate kind of chiral molecule. Okay, for example, the phosphorus and the sulfur. Okay, so phosphorus, if you have 3 different attachments. Okay. And then plus this lone pair electron actually can treat it as the 4th attachment, 4th substance group. Okay, and then you generate kind of the chiral centers. Okay, and then this molecule will be stereo. Okay, it should be kind of chiral. Okay, and same thing for the sulfur. Okay, sulfur also the lone pair electron. You can have 3 attachment. Okay, so that will be chiral. Okay. There are many more, okay, but not nitrogen, okay, not nitrogen, okay. So here kind of good question, okay. So for nitrogen, okay, so there's lone pair electrons, okay, and then you can have the 3 attachment, okay. So looks like nitrogen can also be the stereo centers, okay. But at room temperature, okay, so nitrogen structure can quickly flip, okay. So going like this way, okay, so going up, okay. And then you generate it in enantiomer, okay. All right, okay. So because this quickly free up, okay. So you have these 2 enantiomers, okay. 1-to-1 ratio in the solution, okay. So that's we call it the racemic mixture, okay. So that's could be kind of should be achiral, okay. So achiral, okay. So not nitrogen, okay. So But yeah, for the phosphorus and the sulfur, okay, so yeah, the energy barrier can too high, okay, so there's no flip, okay, so that's why you can have only one yeah, the enantiomers in the solution, okay, so no nitrogen, okay, so no nitrogen, okay, so nitrogen because the yeah, nitrogen inversion, called nitrogen inversion, okay, so that's yeah, no yeah, steric centers, okay. For you guys, okay, just keep in mind, okay, carbon, silicon, phosphorus, and then sulfur, that's it, okay. Okay, so there are another situation, okay, so yeah, there's another situation, okay, there's no chiral centers, okay, so yeah, no carbon kind of yeah, silicon or kind of phosphorus kind of chiral centers, okay. The whole molecule also be chiral, okay. For example, yeah, this is aniline, okay, adenine, okay. So adenine, okay, so yeah, the center carbon is kind of sp hybridized, okay, and then the two terminal carbon sp2 hybridized, okay, because they are kind of yeah, special arrangement of yeah, pi bond, okay. So the yeah, two terminal attachment, okay, so yeah, the two hydrogen on this carbon and two hydrogen on this carbon, okay, actually not in same plane, okay, so they are in a plane kind of perpendicular to each other, okay, so yeah, here's kind of in the plane, it's kind of going out, going out, going inside, okay, so yeah, if we change these two hydrogen, okay, to some other substance, okay, there's possibility we generate kind of chiral molecule, okay, so for example, yeah, we just change one two of hydrogen into a COH, okay. And then yeah, if you yeah, get this kind of mirror image, okay, so that's it's a mirror image, okay. So you find okay, these two will be non-superimposable, okay. Non-superimposable, okay, so that should be a pair of enantiomers, okay. And for reality, okay, for this molecule, you cannot find any simply plan cut through this molecule, make half mirror image to another half, okay, because you do this, okay, one going up, one going outside, okay. Whatever you try to do, okay, so no way you can get kind of simple plan, okay. So that's means here that yeah, this whole molecule will be chiral, okay. So that's very special case, okay. There's no chiral carbons okay, in the molecule, okay. So because all the carbon, okay, so here's kind of just here the sp2 hybrids, okay. So yeah, won't be kind of chiral carbons, okay. But the whole molecule is chiral, okay. And so there's another special case, okay. So helical kind of molecule, okay. So yeah, for example, yeah, this is hexene case. So yeah, so that's here 6 yeah, the benzene case. So yeah, yeah, next to each other, okay, but here the terminal two benzene kind of here the yeah, broken, okay. And then whole molecule case, so not planar case, so actually kind of here the yeah, there's helical structure, okay, like this, okay. So yeah, they see the helical structure, okay, so yeah, you cannot find a symmetry plan to it, okay, so that's yeah, whole molecule is chiral, okay, if it's kind of yeah, huge the yeah, specific rotation, okay, so 3000 something, okay. So. And one of the most famous helical molecule kind of yeah, the chiral is the DNA, okay, so yeah, that's yeah, the yeah, whole molecule kind of chiral, okay, so it's right-handed, okay. All right, so that's yeah, we done the lecture today, okay, so in the end, okay, so we do a little bit of practice, okay. And the first practice, okay, so we have 3 molecules, okay, so yeah, find all the chiral centers, okay, so also called steric centers, okay, and then RS to them, okay, so that's the one of the most common question, yeah, we'll see the chapter 7, okay, then RS, okay, so no matter this molecule show that yeah, the Newman projection, or show that kind of yeah, Fisher projection, or kind of restructure, or whatever, okay, so you should able to then RS, okay. And second question kind of yeah, naming question, okay, give you name, ask your George structure, or give you structure, ask you kind of yeah, give you the name, okay, so that's yeah. Also yeah, you'll see the yeah coming exam, okay. All right, so yeah, we just yeah use the last couple minutes yeah practice on these questions, okay. So yeah, if someone like you can also turn on yeah, the chat window, okay. No chat window, turn on the annotation yeah function, okay. So yeah, label RS yeah for the yeah steric centers yeah for this yeah the 3 molecule, okay. Take a try, okay. Yeah, someone already take a try, okay, good, okay, go ahead, okay. Yeah, for the yeah, Newman projection, okay, little bit careful, okay, so yeah, that's yeah, sometimes kind of yeah, you have to yeah, develop the view, okay, so yeah, make sure that the hydrogen point away from you, okay. Okay, anyone want to try this here, the yeah, ring structure, and also the yeah, this yeah, Fisher projection, okay. Okay, so we are done at the chapter 7, okay. So here we talk a little bit about the exam 2, okay. So exam 2 will cover chapters 12, 6, and 7, okay. Relatively tough, yeah, the yeah, kind of exam, okay. So yeah, So in this case, I want to give you guys a little bit more time to study, okay? So the two possible dates for the exam 2, okay? So either this Friday, okay, or maybe next Monday, okay? And here's a pool, okay, for you guys, okay? So so either this Friday, okay, or next Monday, okay? So if this Friday, okay, so there's no class for this Friday, okay. If the next Monday there's no class for next Monday, will both become the class will become discussion, okay. So become officer, okay. Right, okay. So just make your choice, okay. So exam 2 will based on the smart work, okay, based on smart work, okay. So I will open it here probably from 6 until 11, okay. So you have 5 hours, okay. So to work on it, okay. All right, okay. So all right, okay. So just another pool, okay. Show you guys, okay. All right, similar like this morning, okay. So majority students, okay. So want to have exam, okay, on Monday, okay. That's fine for me, okay. So in this case, we'll have exam on Monday, okay, next Monday, okay, and then no class, next Monday, okay. Anyone want to try the last one? Okay. So last one, okay. So is feature projection, okay. So keep in mind, okay. So you have to make sure that horizontal bond point towards you, okay. So in this case, hydrogen actually kind of this hydrogen point towards you, okay. And then when you give kind of draw the arc, okay. So give assignment, okay. So for example, the first one, okay. So highest priority, OH, okay. And then this branch should have high priority because this carbon has two oxygen, carbon and oxygen, okay. And then also this has got another the carbon attached to it, okay. So that's the higher priority, okay. So if you draw the arc, okay, so 1, 2, 2, 2, 2, 3, okay. So that should be kind of looks like counterclockwise, okay. So then point, okay. So that's we learn the Newman projection, okay. Newman projection, okay. So one important thing, okay. So here, okay. Horizontal bond kind of coming out of the page, okay. Vertical bond kind of come back to page, okay. So that's rule for the Newman feature projection, okay. So don't forget it, okay. So here. Okay. All right, okay. So because of time limitation, okay. So I gave you the answer for these 3 questions, okay. So here the front carbon should be S, back carbon should be R, okay. And then here both carbon should be S, okay. And then for the Newman feature projection case, top carbon R, bottom S, okay. Make sure you know how to write RS, okay, for this molecule, okay. Probably next day, okay. So I will Wednesday class I will go through these 2 questions, okay. Those 2 kind of more difficult, and I will go through these 2 naming questions, okay. All right, okay. So that's for the class today, okay, and.